All right, so this is the first of two parts of these lessons on optimization problems, which finishes this unit on applying differential functions. After this, for the next unit, we introduce the idea of an integral calculus. So, with that said, I don't feel like reading through all these bullet points here, but as you can see, these are suggested steps to solve an optimization problem, and I'm going to go through 3. And in general, I'll work through these steps. I will say probably, maybe more so than a lot of the last few lessons, most of your work will not have to do with differentiating. Most of your work is coming up with a way to model the problem, a way to perhaps simplify a function so that you can differentiate it. Quite often the actual differentiation part is fairly quick, and then working with that derivative to figure out how to solve the problem. But most of our work in this is actually not the process of differentiating. It's everything else around it. And so I'm going to have 3 problems here, and we'll look at some more for the other part of this lesson. So here's an example of an optimization problem. You have 2,400 feet of fencing, and you want to create a rectangular enclosure along a straight river. And so let me have a quick little diagram. This is kind of a standard type of question. So here's a river, conveniently straight, and I want to create a rectangular enclosure, which means I want to create an area that's a rectangle. So something like this. And the perimeter of this fence, which has 3 sides, is 2,400 feet. Now if it's a rectangle, that means, again, I have 2 sides of the same here. I'll call these y, I'll call this x. And the area of this is x times y. And again, I want to maximize that. But I only have 2,400 feet of fencing. Now I'm sure you realize that various rectangles have greater areas than other. The perimeter is a constant, the area is not. For example, if you make a really skinny, long rectangle, it's a fairly poor use of your space. So what's the maximum dimension? What are the dimensions that lead to a maximum area? The perimeter is constant. So with that said, how to approach this problem? Well, let's first, again, I know that area is the same as x times y, but I want to eventually get area down to just a function of one variable, x or y. And the other thing I know is that I have 2,400 feet of fencing. That means my perimeter is 2,400 feet. So I know that 2,400 is the same as 2y plus x. And I also know, as I've written in the diagram there, that area is the same as x times y. So I have 2 equations, both with 2 different variables. I need to get it down to area as a function of one variable, which means looking at this perimeter equation, I can solve for x, I can solve for y. It's definitely a little less work to solve for x. So solving for x, I can say x equals 2,400 minus 2y, which means I can look at my area function, a equals x times y. Again, this is the function we're trying to maximize. But instead of x, I'm going to write 2,400 minus 2y. And this is the function I want to maximize. I want to make this area as great as possible. So now the question is, how can we use derivatives to figure out what the maximum of this function is? Well, if we can find its critical points, then we can find out where it has a max or a min. And all those ideas from curve sketching, which we spent several days on, all apply to finding max and mins of functions, and that will lead to, in this case, a maximum area. So I want to differentiate this. Now in this case, well, it's not terribly hard to differentiate this as is. It's a bit easier if I distribute the y and write it like this, write it as 2,400y minus 2y squared. So there's function a. Nice, easy function, one of those rare functions at this point that we can differentiate without using really any of the chain rule or product rule or something. So we want to maximize this. So we want to find critical numbers or find critical points. And so derivative nice and easy. 2,400 minus 4y. And again, to find critical points, we look at our derivative and we make it either equal 0 or find where it does not exist. In practice, with optimization problems, I can't think of an example where determining where the derivative does not exist is actually one of the values we want. Plus, in this fact, the derivative will always exist. So again, essentially, you're pretty much always going to make the derivative equal to 0. Solve for y, and you get y equals 600. So maybe I'll move over here. Haven't given myself enough space. So that's the optimal measurements when y, looking at my diagram, is 600 feet. So therefore x is going to be the same as 2400 minus 2y, or in this case, 1200 feet. And there are optimal dimensions. Now if I wanted to find the area, again, the actual maximum area would be 600 times 1200. But again, when the width is 1200 feet and the height of this rectangle is 600 feet, I know that must be the optimal measurements to create the maximum area. And I know that has to be the best because there's only one critical point. Plus, I can just look at this and realize this area function is a quadratic function opening down. I can visualize that critical point will be a maximum anyways. To be honest, you didn't even have to use calculus here. If we recognize that this area function was a quadratic function and it's opening down, you're finding the vertex. And you can use pre-calculus 11 work to find the vertex. That's it. We shouldn't expect to always get such a simple function. Good place to start. Quite often the functions we're differentiating are going to get fairly messy. And in fact, I make a point here that when you're coming up with a function, expect this function to get very messy. And so quite often, the worst thing we can do is try to just differentiate it right away. Quite often, we want to take some time to simplify and factor out constant values before we try differentiating. Often, that makes the differentiating quite easy. In this case, though, this is about as easy as it gets. Okay, this is an easy problem, but a good place to start. Okay, let's look at a second problem. That's still, everything we're going to look at today is relatively easy for optimization problems, but that's where we're starting with it. So let's look at this problem. I have two parabolas, y equals x squared plus 1 and y equals x minus x squared. I'll just label them here. I know this must be x squared plus 1, not only because it's in red, but because it's a parabola opening down. Up, this is a parabola opening down. Determine the shortest possible vertical distance between these two parabolas. So let's visualize what's happening here. So I'm looking at these two parabolas, and for example, I've shown this sort of distance here. Okay, and I'll call that distance d. That said, I'm pretty sure that's not the shortest possible vertical distance. I'm guessing it's somewhere around here, or is it there? Somewhere around here. But where is it? And what is that distance? But somewhere in there, I can just tell by looking at it, by eyeballing it, that that must be the shortest distance. But where is it? It's hard to really tell, actually. Is it right there, or is it right there? I can't really tell yet. Plus, I don't have any numbers labeled on this axis anyways. But that's the idea. I want to make that as short as possible. All right, so how do I do that? Well, that distance that I've highlighted there in yellow is the difference between the y coordinates of these two functions. And really, the function in red is always greater than the function in blue. So that distance, if I want to keep it positive, which I want to keep it positive, is always going to be the same as the output of x squared plus 1 take away x minus x squared. And so the distance that we're trying to minimize is always going to be the same as the output of x squared plus 1 minus the output of x minus x squared. All right, so let's clean this up a bit. Combine like terms. Now I get 2x squared minus x plus 1. And this is the function I want to optimize. In this case, I want to minimize this. Again, maximizing the function is kind of silly. If I want to find the maximum distance, I can know there is no maximum distance because the more I go this way or this way, this vertical distance just keeps getting longer and longer forever. So there is no maximum distance. The distance gets infinitely large as I go on and on to the left or the right. But I can tell there's a minimal distance. So where is it? So now again, I have a quadratic function. I can tell this quadratic function is opening up, which means there's only going to, there's only going to be one critical point. And since it's a distance is a quadratic function opening up, I can visualize quickly that one critical point is going to be the minimum of the parabola, which means it's going to be the minimum distance. And so I can really quickly figure that out by differentiating this. So d prime is equal to 4x minus 1. All right, that means, again, I want to find my critical points. So make that equal to 0. Find where that vertex is, which means x equals a quarter. And so that's my x coordinate. When x is a quarter, when x is 0.25, these two functions have the shortest possible vertical distance between them. But the question was actually asking, what is that shortest possible distance? And so let's find the shortest distance. I just need to take that 1/4 and substitute it into here. Because the question was actually asking, what is that shortest possible distance? So the shortest distance. And so you get 7/8. And so that's the shortest distance when x is 1/4. Notice again, both these questions have had very little algebraic work. Again, I'm starting with more straightforward optimization problems. And notice for each of these, I knew there had to be some sort of optimal, in this case, distance, shortest distance. And using a derivative, I was able to figure out that quite quickly. All right, last question. Again, another standard type of optimization question. A box with an open top is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each of the 4 corners. So I want to visualize the situation. So let's do that first. I have a square. It's a nice shape to draw. And I say each side is 3 feet, so let's put 3. It says we're cutting out a square from each of the 4 corners and bending up the sides. And this will create an open top box. A fairly straightforward idea. Imagine I cut out a square here. And each of these, squares has to be the same, or else it won't create a nice tidy prism. Fold up these sides here, and you have a very, very simple 3-dimensional prism. Right, an open top box. Okay, so I've visualized the situation, and I've labeled the side of each square that I'm cutting out, because again, I'm cutting out these squares to create this object. I've labeled each of those x. So determine the critical numbers for this function. Sorry. One thing I haven't done yet is determine volume as a function of x. All right, so the volume of this prism as a function of x. So if I look at this prism, volume is the same as length times width times height. Pretty straightforward. In this case, what's my length, width, and height? Well, if I look at my diagrams, I can see that this distance from here to here must be the same as from here to here, because I started with a square that I cut squares out of. And the distance either of those is the same. But what is the distance? It's not 3. It's 3 minus those squares, 2 squares I cut out from each. So each of these is going to be 3 minus 2x. Right, that's that distance from here to here. That distance I'm drawing in green is 3 take away those 2 x's. And so I have 2 of those. So 3 minus 2x times 3 minus 2x times the height. And the height of this is the exact same as x. And so therefore the volume of this function is 3 minus 2x squared times x. Or I'll put the x first. All right, there's the volume of my function. That's it. Now I've done that second part. Determine an equation that represents the volume of the open top box. V is a function of the side length. So now determine the critical numbers of this function and explain what they represent. So I want to find the critical numbers of this function v. Now I can differentiate this right now. I would use the product rule and the chain rule. But if I just do a little bit of grade 10 algebraic work, I can get it down to something much simpler in my opinion. And for example, this here, it's a perfect square binomial, so I know the 3 terms are going to be 9. The first term is going to be 9. The last term is going to be 4x squared. The middle term is going to be 3 times negative 2x times 2. So negative 12x. Well, that's times x. Distribute the x. All right, so now that was, quite quick to do. Differentiating that, it's tough to make a mistake now differentiating that. So the derivative of that is a quadratic function. So there's the derivative of the volume, and I want to find the critical number, so I want to make this equal 0. And solve for 0. Now, this is a quadratic function. If we can factor this, then we can find the solutions really quite easily. And the first thing I probably want to do is take out a greatest common factor, which the greatest common factor is 3. And I'll rearrange these terms to put them in a more familiar order. Right, and if I can factor that, then it's way faster than using the quadratic formula. And I can factor that. 2 factors into being 2x minus 3 and 2x minus 1. Which means, if I analyze my factors, I can see my 2 critical points. When x equals 3/2 and when x equals 1/2. Okay, so I have 2 critical numbers here. So I found my critical numbers. What do they represent? Well, for this, they, think about what we did with curve sketching. They both, they are critical points. They don't have to be a max or a min. Depends if it's increasing or decreasing around there. And there's various ways I can determine what these are. However, one thing that's fairly easy to do is I know these are critical numbers. I know they're important numbers here. And so if I just put these back into my volume function, any of these steps right here, let's find out the volume for each of these. And that'll give me a good sense. For example, if I put 3/2 into the volume function, I get out 0. It's probably most obvious if I look at this step right here. Replace x with 3/2, you get 3 minus 0. Sorry, you get 3 minus 3, which is 0, and 0 squared is 0. And so 3/2, when x is 3/2, the volume is 0, which means that must be a minimum. And again, if I look back at my diagram, that makes complete sense. If x is half of 3, if x is 1.5, that means I'm cutting out squares this big. There's one square, there's another square. And that means I've cut out the whole thing. There's nothing left to fold up. And so it is a critical point. It's the minimum. It's one of our minimums. I can't, essentially you can't cut out more than 3/2. And so I can see right away that when x equals 3/2, that critical point is a minimum. So the volume is 0. So that will lead me to believe that when x is 1/2, that's probably a maximum. And again, when x is 1/2, that means I'm cutting out half a foot here, half a foot here, half a foot here, half a foot here. Put 1/2 into any of these functions, whichever one looks easiest to you. I think this is still probably the nicest one to deal with. Put 1/2 into there, and you get out exactly 2. And so that must be the absolute maximum. That must be the maximum volume you can create with this piece of square, what was the dimensions? Square cardboard, doesn't really matter. And so in this case, while I could have found the intervals of increasing and decreasing, that may have been fairly quick. Just plugging the numbers into the function here is also pretty quick. And so let me kind of finish answering the question then. So I'll say when x equals 3/2, the volume equals 0 cubic feet. So the volume is maximized. Sorry, it's minimized. Oh. Which again, please don't lose sight of how silly it is to really have to use calculus to figure out if you cut out squares so big that there's no material left. Obviously, you'll have no volume, but that's just confirmed. A little more important is probably this point. When x equals 1/2, the volume equals 2 cubic feet. And that's when the volume is maximized. And because I know there's no other critical points, I know there could be no other, there could be no other greater maximum volume than 2 cubic feet. Because if there was something greater, if it went like this, and if, let's say, looking at my volume function, if this is where it had 2 cubic feet, if it went back up again and there was another part, then there'd have to be actually 2 more critical points. And again, there's no more. All right, so while there's still more to do on optimization problems, and all of these problems today had actually pretty pleasantly simple polynomial functions to work with, it does kind of set a good, I think, a good start for what an optimization problem is. But I don't think I'm surprising you to say that the functions can get a lot messier than this. With that said, good place to stop.